Hello everyone, and welcome back to Mitchell's Physics Review. Today we are working on electric potential. Let's take a look at our problem. Two insulating spheres have radii 0.3 centimeters and 0.5 centimeters, masses 0.2 kilograms and 0.7 kilograms, and uniformly distributed charges of -2 microcoulombs and 5 microcoulombs. They are released from rest when their centers are separated by 1 meter. First, let's take a look at our givens and draw a picture. For our givens, we are given that they are separated by 1 meter. They're both insulators, and then we can separate even further into the givens for sphere 1 and sphere 2. For sphere 1, we're giving the radius is 0.003 meters, a 0.2 kilograms, and has a charge of -2 microcoulombs. For sphere 2, we are given a radius of 0.05 meters, the mass of 0.7 kilograms, and a charge of 5 microcoulombs. Now we can draw a picture of what we have been given so far. 1 meters in distance, 2 insulating spheres, their radiuses, and this is before the collision, which we'll get back to in part A. Now for part A, how fast will each be moving when they collide? First, let's take a look at what they're going to look like after the collision. As we drew our picture before, we were given that distance, but after the collision, notice that the distance will no longer be 1 meter. Instead, it will be the distance between the two radiuses add together. So here's our picture for after the collision. Now we can look more at this mathematically. We know that energy is conserved in this case, so we can set the initial energy equal to the final energy. In this case, we have electrical energy is equal to kinetic energy. For electrical energy, we have one in one way and one in the other, so we have Ke Q1 times Q2 over D minus Ke Q1 times Q2 over D2, which is this new distance between the spheres after the collision is equal to the kinetic energy of sphere 1 plus the kinetic energy of sphere 2. Now, so we don't have to worry about the negative signs on our charges, we can say Q1 is negative and make this a positive, and we can say Q1 is negative and make this a negative. From there, we can simplify our equation a little bit by taking out common terms. So we have Ke times Q1 times Q2 multiplied by the quantity of -1 over D plus 1 over D2 is equal to 1/2 mass 2 times velocity 2 squared plus mass 1 times velocity 1 squared. From there, we can plug in all of our givens. You're about to realize we have an issue. We have two unknowns in this problem. So, how are we going to get past that? Well, our first thought should be a collision. Whenever we hear that word, we know we will most likely be dealing with momentum. So let's take a look there to see if we can substitute in for one of our unknowns. We know that the change in momentum is equal to 0 because momentum is conserved in this case. So we are able to set the momentum of the first sphere equal to the momentum of the second sphere. In other terms, mass 1 times velocity 1 is equal to mass 2 times velocity 2. We can plug in the given masses, and then we can find what velocity 1 is equal to. Now that we know that, we can go down and we can plug that in for velocity 1. Don't forget to square it. From there, it's a plug and chug in your calculator. We're going to multiply and square everything out. So we can start by squaring and adding these two, and then dividing, and then we're going to multiply the rest, and multiply it by 2 to get rid of that half, and from there, we're going to square root everything to get rid of this square on V2, and we get that V2 is equal to 2.66 meters per second. From our equation we found from our momentum, we know that V1 is equal to 3.5 times V2. So we can plug in what we just solved for V2, and we find that V1 is equal to 9.32 meters per second. Now let's look at part B. If the spheres were conductors, would the speeds be greater or less than those calculated in part A? Well, what do we know about conductors and insulators? We know that in conductors, electrons are able to move more freely than in insulators. So how will that change the speeds, or will it affect it at all? Well, actually, it will make the speeds greater. Why is this? This is due to polarization. Like we just said, in a conductor, the electrons are able to move more freely about the surface of the sphere. So, the positive charges will go to one side and the negatives will go to the other, causing the other to change so that they will attract. This attraction force will make them have a greater speed when coming towards each other. Overall, what I struggled with most this video was remembering that when we hear the word collision, we will most likely need to use momentum. I was very stuck when I had two unknowns, so sometimes it's easy to forget when you have a lot of moving parts, especially when with this equation with so many different pieces that are simple and basic rules, like if we're working with the collision, we're most likely dealing with momentum, and how to substitute in values when we have two unknowns. I hope you learned a lot this video, much like I did. Have a great day.